Happy New Year, my dear children. Good morning. So, celebrate this year with health, joy, happiness, knowledge, and all. Happy New Year once again. We'll start our chemistry online class.
We'll see the factors affecting chemical and physical equilibria. We know if a system reaches its equilibrium means the rate of forward reaction is equal to rate of backward reaction. If any changes in these factors happen, the equilibrium will change. The factors are concentration, pressure, temperature, and effect of catalyst and effect of addition of inert gas. So if any of these factors changes, the system will try to remove that change. So this is defined by a scientist called Le-chatlier, and he made a principle. His principle is known as Le-Chatelier's principle. So according to Le-Chatelier, if a chemical system at equilibrium experiences a change in concentration, temperature or total pressure, the equilibrium will shift in order to minimize that change or to counteract the changes. That is, if any change in the pressure, temperature, concentration happen to the system will try, so the equilibrium will distorted. So the system will try to attain equilibrium again. So it will forward some reaction to minimize the change happen to the system, and it want to come back to its original state. We also same, the equilibrium is also same to like the as if sometimes we didn't like changes, so we will try to come back to our original stage. So we also try similar to that, if any changes in equilibrium experience change in concentration, temperature or pressure, the system will try to minimize that and will come back to its equilibrium state. This principle is known as Le-Chatelier's principle. So we'll see one by one. So first we'll see change in concentration. So in change in concentration, according to Le-Chatelier principle, when a reactant or product is added to the system, it shifts away from that added component. So for example, if reactant is added, what will happen? If the concentration of reactant is increased, the system will try to reduce the concentration of the reactant. So it will helps, or it will, how it can reduce the amount of reactants? By reactants react together to give products. So there will be the production of more products. The system shifts towards the removed component. So for example, if you change, look here, if increase in the concentration of the system of any of the reactants. So if the reactants concentration increases, the shifts to the equilibrium to the forward reaction, that is formation of product. So if increase the concentration of any of the products, equilibrium shifts to the backward reaction. So products will convert to reactants. If reactants concentration increase, equilibrium will shift to the forward reaction, that we will get more products. If the concentration of product increases, what will happen? The backward direction reaction will be forward. This is the example for the change in concentration. We will see the change in pressure. So again, you can see an example for change in concentration. What happens if the concentration of CO is increased in this case? So this is the reaction of carbon monoxide reacted with the hydrogen to give methanol. So what happens, the concentration of carbon monoxide is increased here. So we know carbon monoxide is the reactant here. So according to Le-chatlier principle, the extra carbon monoxide must be used up. That is, the extra carbon monoxide must be used up. So it is used, so it is reacted with more hydrogen here, and we will get more product. So the hydrogen consumes more carbon monoxide and it will produce more methanol. So we'll get more products. So in any industry, if we want to prepare more products, like this method we can use. Increase the concentration of the any of the reactant, we'll get more products. We'll see next one. So the forward and reverse reversion rates adjust until the again and equilibrium. So the reaction will continuous up to reaches the equilibrium again. So if a system is in equilibrium, if any changes in the concentration, so it want to come back to its original position. So it will try. For example, here you can see, if carbon monoxide increases, H2 will decrease because that much H2 will act with carbon monoxide and the product will be increase. So K will be remains constant because product also increasing here. According with the reactants, product increases. So the equilibrium constant remains constant. So the next one is change in pressure. We will see what will happen with the change in pressure. According to Le-chatlier principle, if the volume decreases, the concentration increases, and there will be a shift to the side with a less amount of moles. The pressure and concentration volume will, there is a relation between them. If the volume increases, the concentration decreases, and there will be shift to the side of the more amount of moles. So pressure increases, according to that the volume decreases. Pressure increases, volume decreases. Pressure increases, volume decreases. Pressure decreases, volume increases. So, if a decrease in pressure, the equilibrium will shift to the larger number of gaseous molecules. That is, that we will see by the example. If in the increase in the pressure, the equilibrium will shift to the lesser number of gaseous molecules. That we will see by an example, then it will be clear. For example, we will see with the Haber process. Haber process is the production of ammonia. Nitrogen and hydrogen combine together to give ammonia. This is known as Haber process. So we'll see with the Haber process. So in the case, if the pressure of the system, this ammonia and hydrogen which give nitrogen and hydrogen which give ammonia, if any changes in the system, if the pressure increases in the system, the increased pressure reduced by reduce the number of gas molecules. If there are more number of gas molecules, then there will be pressure will be more. So if any increase in the pressure, the system will try to reduce that pressure by shifting where the lesser number of molecule to that side it will shift. So if we check here 4 moles of, for example, here 1 nitrogen and 3 hydrogen. So totally 4 moles of reactants are there. So only 1 mole of ammonia is there. So equilibrium will shifted to here, this side. You can see it will here, the bigger arrow. So the equilibrium will shifted here, where will be the less number of moles. To that side equilibrium will shift. So when pressure is decreased, so that is the in the case of pressure increase. If pressure decrease, what will happen? So if pressure decrease, the stress of decreased pressure is reduced by increase the number of gas molecules. It's ulta, vice versa. There are two products of gas molecules. For example, if you check here, PCl5, which gives PCl3 and chlorine. So thus the reactant shifted to the products, because here 2 moles of reactants are there, so it's shift to here. The next one is change in temperature. So according to Le-Chatlier principle, we know there are two types of processes like reactions, exothermic reaction and endothermic reaction. Exothermic reaction means that produces heat produced reactions. Um, so adding energy shift the equilibrium to the left, away from the heat term. Endothermic reaction absorbs energy. Heat is reactant here, so the system will absorb the energy. So this we will understand by this one. So decrease in temperature shifts to the equilibrium in direction of exothermic. If temperature decreases, exothermic reaction will forward. If heat increase, what will happen? System will absorb the extra heat. So endothermic reaction will favor. So if heat decrease, if the system's heat decrease, so it will be exothermic reaction favored. If increase in temperature, endothermic reaction will favor. So we will see this one with an example. This is again Haber process. Here the heat produced in this Haber process is given here, that is minus 92.4 kilojoule mole inverse. So if increase in the temperature brings a net change in the equilibrium state in the direction where this extra heat is consumed. If the heat increases, if we add heat, it will shift to the reactant side. That is the which reaction? Heat increases, that will favor endothermic reaction. So here endothermic reaction is the formation of nitrogen and hydrogen from ammonia. If remove heat, shift to products. Okay, this is the example. So for that is in the case of endothermic reaction. If for exothermic reaction, according to Le-Chatlier principle, in the case of endothermic reaction, so you have to know what are the exothermic and endothermic reaction that we have seen about exothermic reaction. So here is for endothermic reaction. In the case of endothermic reaction, nitrogen and oxygen which give nitrous oxide. Here, so for exothermic reaction, the heat will be minus. Exo, the sign will be minus. For endo, the sign will plus. So from this, you have to identify which will be endo, which will be exo. So if the temperature is increased, what will happen? The added heat will be absorbed by the reactants. These reactants will absorb the extra heat and it will produce more product. So if add heat, shift to the products. If remove heat, shift to the reactants. This is the example. So the next one is effect of catalyst. The catalyst will not have any effect in the changes in equilibrium, but it helps to attain equilibrium easily. So here in the graph, you can see in this graph, this one is the reaction without catalyst. The reactants required activation energy to, it needs certain amount of energy to produce certain amount of product. So if we add catalyst, the green line shows the catalyst. So here you can see the activation energy is in this case is very high, but in the case of if we add any catalyst such as nickel, platinum, palladium, these all are catalysts. Any catalyst, it will reduce the activation energy, so easily can form the product. What we can say is catalyst helps to attain equilibrium easily. Other than that, there is no effect of catalyst on the equilibrium. The next one is effect of addition of inert gas. Um, Inert gas is a substance that is not reactive with any species. We know the noble gases are inert gases. So there is no effect of in the equilibrium. If you add any inert gas, there is no equilibrium. So it's if the substance react with any species in the equilibrium, then there will be a shift. So addition of inert gas, there won't be any changes because inert gases are inert. They won't react with anything, so there won't be any change. So what are the applications? So if we add reactants, we will get more products. In the case of a Haber process, if we add more ammonia, that is we are checking with the Haber process. If we add more any of the reactants, we will get more product. Then forward reaction produces heat, reverse reaction absorbs heat. These all things are given here. If we remove products, the forward reaction again increases. Decreased temperature, increased pressure, all have a certain uh, uses. So for optimal condition for the process production of ammonia is low temperature and high pressure. If you apply low temperature and high pressure, we will get a good yield of ammonia. So for a quick revision, here the given changes are given here. So for example, we'll check with a question. Here a reaction given sulfur and oxygen reacted to give sulfate, and here the plus sign is given. So for the plus sign it is endothermic reaction. So certain things are given. If oxygen gas added, we know oxygen is a reactant. So what will happen? If the reactant increase, it shift towards the product. So the forward reaction increases, will get more product. So the reaction vessel is cooled. If it is cooled, we are reducing the temperature. So what will happen? It is an endothermic reaction. So shift to products. So we have seen this in the endothermic process. The size of the container increase. If the size of the container increase, what will happen? Volume increases, pressure decreases. So shift to more particles. Where more particles there? Towards that side it shift. For example, if we check, there are 1 plus 13 reactants, 13 moles of reactants, 8 moles of product. So it will shift towards to the more particles. So shift towards the reactants. If sulfur trioxide is removed, that is our product. If we remove product, the equilibrium will shift to get more products. A catalyst added to make it faster, there won't be any change. So this is a example. Such questions you can expect for your examination.